All right. Okay. Hello, everyone. Welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube, and you can find the link on our website and also on our Twitter. This week, we will have Ethan Nadler, a PhD candidate at Stanford University, to talk about dwarf galaxy dark matter microphysics constraints. Ethan, thank you very much for coming. Whenever you're ready.
Great, thank you. First thing I'm going to do is cut my video just in case my connection becomes unstable, but I'll turn it back on later. Hi everyone, I'm Ethan Nadler. I am a final year, going into my final year of my PhD at Stanford. I mainly work with Riso Wexler at Stanford, but I work with a whole host of other people on the dark energy survey as well, as I'm going to tell you about. So I'm going to be talking about constraints on the properties of dark matter using the faintest galaxies in the universe. I have about 40 slides, and hopefully we can have a lot of discussion. So please feel free to stop me. I'll try to keep an eye on the chat as well. Okay, so let's get started. So I wanted to start with this cartoon. This is a drawing by Tim Tate, and it shows the landscape of candidates, of particle physics candidates for dark matter. And I find this cartoon to be very nice. I mean, it shows us that, even though we know that dark matter constitutes, roughly a quarter of the energy density of the universe, and even though we know that dark matter is cold and collisionless, at least on scales comparable to the size of the universe, we actually have very many theoretical ideas about the particle nature of dark matter. And each of these ideas has, distinct physics associated with it. So the first time I saw this, I found the cartoon kind of worrying in a sense. I mean, it's very hard to build, a dedicated experiment to look for all of these distinct types of physics, to build experiments for each one. And so I think a useful question from an astrophysical and a cosmological perspective is, what guiding principles are there? How can we kind of sort out all of these different types of dark matter candidates using as few measurements as possible? And I think from this kind of cosmological perspective, there actually is a very kind of useful operating principle that lets us separate many of these models. So this is a plot from this very nice review paper by Buckley and Peter. And it's showing many of those dark matter models from the previous slide in this parameter space of the coupling to the standard model on the x-axis. And on the y-axis is essentially the minimum halo mass. So the mass of the smallest gravitationally bound dark matter halo at which the physics of dark matter has an observable impact relative to a cold collisionless model. In particular, if we can measure, say, what is the smallest mass halo in the universe, so if we can draw a horizontal line somewhere on this plot, then you can see that we actually rule out a large number of dark matter models, and we go some way to detecting what it actually is at a particle level. So in general, the microphysical properties of dark matter affect the formation of structure on very small scales, and that's what I'm going to be focusing on in this talk. So another way of looking at this is in terms of the matter power spectrum. So this is probably a plot that many of you are very familiar with. It's the matter power spectrum as a function of inverse scale, or as a function of the cosmological wave number k, which shows basically the clustering of matter on different length scales. And the matter power spectrum has been measured very precisely on large scales using the cosmic microwave background, so by missions like Planck. And going to successively smaller scales, it's been measured by the clustering of galaxies from the Lyman alpha forest, and also using weak gravitational lensing. And so the question I'm going to be kind of posing in this talk is, how can we push these measurements to really extremely small scales, so physical scales smaller than a megaparsec. And I've kind of illustrated this in a cartoon here. So I've extended this black CDM line with some fixed cosmological parameters down to these really small scales. And I've shown three kind of cartoon sketches for what the microphysics of dark matter can do to this function. And I'm going to talk about these in much more detail later. But generically, you see that, depending on the choice for the dark matter model, you actually have very different signatures on these small scales. So small scales contain information about dark matter physics. They have to in a physical sense. And so we have to search there. And I think a very natural question to ask about these small scales, or about matter that is clumped on these small scales, is, for the very smallest halos, what is their luminous content? And that's what I'm going to be focusing on. So my talk is split into two parts. In the first part, I'm going to be talking about this question of the luminous content of the smallest halos. And then I'll turn to the implications of these measurements that we've made for the physics of dark matter. Okay, so to set the stage to answer this question about the luminous content of small halos, this is a plot from a review paper that shows essentially the galaxy halo connection. So the x-axis is the mass of gravitationally bound dark matter halos over many orders of magnitude, and the y-axis is the stellar mass of the galaxies that live inside of these halos, normalized by their halo mass. So you see, at say very massive halos at 10 to the 15, we know the types of galaxies, these kind of large elliptical galaxies that live inside of them very well. And in general, this very simple hypothesis that less massive halos host fainter galaxies fits the data very well. And in fact, what we've learned is that there's a really rich set of feedback processes, of astrophysical processes like AGN feedback or supernova feedback, that set the shape of this stellar mass halo mass relation over many orders of magnitude in halo mass. And so there's kind of a question, and the question is, what happens at this extremely faint end, which is another way of asking what is the luminous content of the smallest halos that we can hope to detect. And this kind of regime it's really largely unknown what happens. It's thought that reionization effectively shuts down star formation in systems below some critical halo mass. So these are not actively star forming galaxies, and they probably have very low stellar to halo mass ratios. But the observational constraints in this regime are largely lacking. And that's due to a very simple reason. And the reason is that in order to detect those very faint galaxies, we have to look nearby. And that's purely an observational bias, if you like. So this is a plot of every known galaxy in the universe as a function of the distance from us in megaparsecs. So going out to 6 megaparsecs, this is quite a small scale. The y-axis is the brightness of the galaxies, with brighter systems like our own Milky Way towards the top. And so what you see in this plot is that the very faintest galaxies, right, in order to detect the very faintest galaxies, you really have to look close. So there's this very clear kind of observational locus of galaxy detectability. And in particular, the extremely faint galaxies, so the ultra faint dwarf galaxies, all of them that we know of are actually satellite galaxies of the Milky Way living inside the Milky Way's dark matter halo. And those are the systems that occupy the very smallest luminous dark matter halos that we can hope to detect. And that's what I'll be focusing on in this talk. Okay, so the measurements of the Milky Way satellite population are actually quite exciting these days. This field has developed really rapidly, and I'll try to show you why. So there's this population. We know of about 60 Milky Way satellites today. We've known about roughly 10 of them for a very long time. Those are the so-called classical satellites of the Milky Way, which have stellar masses greater than maybe 10 to the 6 or so. In fact, we knew about 2 of them, the Large and Small Magellanic Clouds. We knew about those since basically prehistoric times, because you can look up in the southern hemisphere, like in Brazil, and see them on the sky. In the 1900s, these systems were discovered by looking at photographic plates, looking for stellar overdensities in photographic plates. And then something really interesting happened when Sloan brought digital imaging to a large region of the sky. This kind of automated, to some extent, the search for these very faint stellar overdensities. And it doubled the population of known Milky Way satellites from roughly 11 or so to maybe 25. And then in the last 5 years, something really amazing has happened. And Essentially what's happened is that several surveys, many of which use the dark energy camera, but also Pan-STARRS, Hyper-C Prime Cam, and so on, have conducted extremely deep photometric searches over large regions of the sky, some of which had not been searched by SDSS. And what they've done in the matter of, as I said, of the last 5 years is they've doubled the population of known Milky Way satellite galaxies again. So we're now near 60 of these extremely faint dwarfs. This is a map of their positions on the sky. And you can see various survey footprints on this map. So the dark energy survey footprint is shown in red here. And so there's a few just qualitative things to note when you look at this map of satellite galaxies. And the first is that DES has, of course, surveys the sky in the vicinity of the Large Magellanic Cloud. And it's actually discovered a large kind of overdensity of satellites there relative to what you would expect from an isotropically distributed satellite population. So that's really interesting, and that's actually evidence. We've shown, as I will talk about, and other groups have shown, that this is evidence of the accretion of satellites of the Large Magellanic Cloud into the Milky Way. So these systems, some of these systems are kind of satellite galaxies of satellite galaxies. Or in the dark matter context, there's subhalos of subhalos. And this is kind of really cool, I think, confirmation of hierarchical structure formation. The other interesting thing about this plot is there are a few of these systems. So for example, the green systems discovered by HSC. And those are actually extremely low surface brightness. So HSC only surveys very small areas of the sky. But when it does so, extremely deep photometric limits, it consistently finds these really low surface brightness galaxies lurking in kind of the outer Milky Way dark matter halo. So close to the virial radius of 300 kiloparsecs. And what that implies, just again, from a purely observational standpoint, is that even this population of 60 Milky Way satellite galaxies is highly incomplete. And we expect to find many more, as I'll talk about. Okay, so if you've followed this field at all, you've probably heard about the missing satellites problem. And I actually recently discovered it's on Wikipedia. So there's a dwarf galaxy problem, according to Wikipedia. And Wikipedia claims that the dwarf galaxy problem is that there seem to be enough normal-sized galaxies to match the predictions of cold dark matter simulations. But the number of these dwarf galaxies that I'm talking about is orders of magnitude lower than we predict. So that's what Wikipedia says. That's a little confusing because then if you start reading papers about it, particularly papers in the last 5 years, the papers consistently say that there's no missing satellites problem. In particular, once you account for just our observational incompleteness, and if you make some reasonable assumption about the stellar mass-halo mass relation, its extrapolation down to these low halo masses, then you really don't find evidence of this extreme mismatch that Wikipedia claims to exist. And then it gets even more confusing. So if you keep reading articles about this, you'll probably see ones like this that say there are actually too many satellite galaxies detected around the Milky Way and that astronomers are facing the opposite problem of what they used to. So this is really confusing. This is how this makes me feel. And hopefully by the end of the talk, you won't feel like this. So what I hope to show you is that there's kind of a level-headed and data-driven approach to answer this question that kind of clears this up. And of course, I will fall strongly in the camp of there's no missing satellites problem, but I hope to show you why that's true. Okay, so as I said, the recent literature largely agrees that if you account for these observational completeness corrections, and if you extrapolate stellar mass-halo mass relations in some reasonable way, then your predictions from just a cold dark matter model are consistent with the number of observed satellite galaxies. But there's a big caveat in most of those claims because most of them have only been demonstrated at fixed modeling assumptions. So say at a fixed extrapolation of the stellar mass-halo mass relation, or in the context of hydrodynamic simulations at fixed assumptions about the subgrid physics that governs star formation and supernova feedback and so on. An example of a hydro simulation is shown in the bottom here. And moreover, this consistency has only been demonstrated for the brightest half, roughly, of the observed satellite population. So usually just using the classical and Sloan satellites. And so this is what prompted us to build the modeling framework that I'm going to tell you about. And this modeling framework overcomes these shortcomings in really important ways, I think. So I'm going to talk about each of these steps in detail. But largely, I wanted to give you an overview for what we do before diving into that. So the idea is to resimulate at very high resolution dark matter halos that we think are like the Milky Way in key characteristics, and I'll be explicit about that in the next slide. And then to overcome this issue of fixed modeling assumptions in this very faint regime, we've developed an empirical model of the galaxy halo connection that applies to these very faint galaxies. That's actually parametric and allows us to essentially marginalize over these theoretical uncertainties in the ultra-faint regime. So the next step is really quite important. So the model that we've built is actually directly tied to photometric data, and in particular to the photometric searches for satellites in DES and Pan-STARRS data. So this allows us to model, really the entire population of Milky Way satellites over more than 75% of the sky. And it allows us to kind of construct an apples to apples comparison with the observed satellite population. So I'll tell you about this in a slide or two. And the important point is that, given these theoretical predictions that can be placed on the same footing as the observations, we can actually perform a statistical inference, right, and fit for the parameters of the galaxy halo connection and infer what that function is doing in the extremely low mass regime. Okay, so that was just a bit of an overview. I'm going to go into more detail now. So the first key point is, how to choose host halos, so host dark matter halos that resemble the Milky Way in key characteristics. And what's allowed us to do this, particularly in recent years, is Gaia. So Gaia has really kind of revolutionized our understanding of the Milky Way dark matter halo. In particular, Gaia measurements of satellite proper motions and of the proper motions of star clusters in the inner halo have allowed a pretty precise measurement of the Milky Way dark matter halo's mass. So the error bar on this quantity used to be roughly a factor of 2, not so long ago, and Gaia has brought this measurement error down to the 20 to 50% level. And if you combine the measurements of these proper motions with measurements of the dynamics of tracers in the inner Milky Way halo, you can actually have a joint constraint on both the mass of the Milky Way's dark matter halo and its concentration. So that's what's shown in the left-hand plot here. So these are both characteristics that we choose our resimulated halos to match the kind of observational errors on these quantities. And another very important point that Gaia has really highlighted is that the assembly history of the Milky Way is a measurable quantity. So in particular, Gaia discovered this group of stars that's kind of kinematically distinct and also chemically distinct. This is in the very interstellar halo of the Milky Way. And this is referred to as Gaia Enceladus, and this has been interpreted as actually the remnant of a large satellite galaxy merging with the Milky Way roughly 10 billion years ago. And this is a really important event, so one of the most important events in the kind of history of the Milky Way's dark matter halo. It's certainly the largest merger it's had in a very long time. And so we choose halos that match the Milky Way in all of these properties. So they are consistent with measurements of its mass and concentration. They experience one of these Gaia Enceladus-like mergers, as you can see in this mass accretion history plot here. And importantly, they also have large Magellanic Cloud-like systems that are chosen to match the real LMC system. So I'm going to show you a movie of this. Hopefully it runs smoothly. Sometimes this can be a little choppy over Zoom. But if it runs smoothly, what you'll see is the following. So the Milky Way is in the center of the screen here. So this is the dark matter halo that will grow into the Milky Way over the course of the movie. There's also an LMC, and you'll see that kind of hanging out and accreting dark matter And towards the end of the movie, it will fall into the Milky Way in a manner that's consistent with measurements of the LMC's actual kinematics. And there's also this Gaia Enceladus fellow. What this does is it merges with the Milky Way quite early in the movie, consistent with when we think the actual Gaia Enceladus event happened, and also with a mass ratio consistent with that measurement. So let me play this. It'll take about 30 seconds. Hopefully you can see it. So this is the merger happening in the middle of the screen with Gaia Enceladus. And then you can see the LMC falling into the Milky Way towards the end of the movie. Okay, so with these ingredients, right, with these resimulated halos that we resimulate at extremely high resolution in order to resolve their subhalo populations, we can start to build a model of the galaxy halo connection. And as I said, this model is empirical, which allows us to kind of parameterize and then marginalize over the theoretical uncertainties in the galaxy halo connection in the ultrafaint regime. So just to be specific, I'll give a couple of examples. So really the first question is how to associate luminosities with the dark matter halos that are found in simulations. Of course, as I should have said, these are not hydrodynamic simulations. These are dark matter only simulations, which allows us to kind of reach the extremely low mass halos that we need. So to answer this question, what we do is we use an abundance matching relation. Essentially what you can assume is that this monotonic relationship between, say, the mass of halos and the brightness of the galaxies that live inside of them continues down to these very faint systems. But we actually allow the slope of this relation, so the faint end slope of the luminosity function and its scatter to be free parameters that we will then fit to the data. So another really important aspect of this is modeling satellite size. And I think, as far as I know, this our line of work is the first to do this, at least carefully, for the Milky Way satellites. And the reason this is important is that observationally, the detectability of these ultrafaint systems is a really strong function of their surface brightness. So it's not just luminosity that controls their detectability, but size plays a really important role. And similarly, what you can do is extrapolate relations that have been fit to kind of brighter and larger galaxies down to the ultrafaint regime, while allowing the power loss slope and the scatter in those relations to be free. So I'm going to show you just an illustration of how this works in practice. So this is that halo that I just showed you the movie of, projected with all of its subhalos plotted, including, of course, you can see the LMC brings many in with it into the Milky Way. So the LMC is actually fixed here to be at the correct position on the sky relative to the DES footprint. And so then what we do is we split this map of subhalos into those that could be detected by, say, DES in red, and those that could be detected by pan-stars in blue, including kind of a self-consistent accounting for like regions of the sky where we can't hope to detect satellites. So you can see that mostly near the galactic disk, there are no colored points, and that's because observationally we can't detect real satellites there, right? So this is kind of self-consistent in that way. And then what we do is we use this model that's been fit directly to the photometric data to predict on a satellite by satellite basis what the detection probability in the corresponding photometric data set is. So that's what's shown here. The color bar shows you the detection probability. And now this map actually doesn't look too different than the map of real Milky Way satellites that I showed you near the beginning. And so what this allows for is, as I said, is a rigorous statistical comparison to the observations. So we do this using an MCMC framework to fit for these parameters that govern the galaxy halo connection. And so I'll just show you a couple of the really important results that came out of this before moving on to its implications for dark matter. So first, what I'm showing you here are luminosity functions. So these are predicted luminosity functions in blue of all the detected satellite galaxies, split into the DES and Pan-STARRS footprints compared to the observations in black. And so the first really interesting thing we found when we did this study is that you really have to have a Large Magellanic Cloud system that is both massive, so with a peak halo mass for the LMC of about 10 to the 11 or 3 times 10 to the 11. And moreover, this LMC must have accreted recently. It has to fell into the Milky Way within the last 2 gigayears. If you don't have these things, then you just won't predict enough ultra-faint galaxies in the DES footprint. So another way of saying this is that what we've done is we've statistically derived evidence for the existence of large Magellanic Cloud satellites. And in fact, the really encouraging thing is that the number of LMC satellites that our model predicts is actually consistent with proper motion measurements from Gaia, which have been used to kind of check on a system by system basis in the DES footprint, which of those are likely to be associated with the LMC. So what we find is that there's really no evidence for a cutoff in galaxy formation due to reionization or due to dark matter physics. In particular, the kind of posterior distribution for that cutoff, which can be visualized as I'm showing here in terms of an occupation fraction. So this is the fraction of dark matter halos that host galaxies as a function of halo mass. This posterior, shown in blue, is consistent with 1. In other words, it's consistent with every halo hosting a galaxy down to essentially the resolution or the detectability limit. So this is actually a really important result for several reasons. In terms of the galaxy formation theory, it's long been predicted that there's a particular halo mass, roughly around 10 to the 8 solar masses, referred to as the atomic cooling limit. And it's predicted that below this mass, atomic hydrogen can't cool efficiently in these halos in the early universe, and that kind of doesn't allow galaxies or stars from forming efficiently in those systems. So our current measurements, right, our current measurement of the minimum halo mass is at 3 times 10 to the 8. So that's essentially the lowest mass halo that we associate with any of these observed satellite galaxies. And so that's, as you see, quite close to the atomic cooling limit. So another way of saying this is that if we detect systems that are any fainter, we will essentially be inferring that those systems formed through the cooling of molecular hydrogen rather than atomic hydrogen. So another way of viewing this is in terms of the stellar mass-halo mass relation. So this is very similar to the plot that I showed you at the beginning of the galaxy halo connection, but it's just not normalized on the y-axis anymore. So this is stellar mass of the ultra-faint galaxies versus the halo mass of the system they live inside. And so, you see that essentially the lack of an observed cutoff translates into just a single power law in this function, right? There's no break at any particular halo mass scale. And the kind of interesting observation about this is we're actually very close to what I would call an observational threshold of what it means to be a galaxy. In particular, if a galaxy has fewer than 100 stars, then even if we think it is a galaxy, it would be very difficult to conclusively say so, because spectroscopic measurements are needed of its population of stars. And with fewer than 100 stars, it's very difficult to obtain like a robust limit on, say, a mass to light ratio and actually call something a dark matter dominated galaxy. So we're very close to this threshold. We're not there yet. But what this means is that we can kind of use these inferences to predict the total number of Milky Way satellites within the Milky Way down to some detectable magnitude limit. And what we find is very consistent with many other recent studies. So we predict that there are about 200 total satellites within the Milky Way. And of course, many of these will be discovered soon. So in particular, the Vera Rubin Observatory is expected to discover really much of the remaining Milky Way satellite population. There's sort of an interesting, maybe worrying point, depending on how you look at it, and that With all of these ultra-faint systems, it's extremely difficult to identify, like on a system-by-system basis, which one is a dark matter-dominated galaxy versus, say, a globular cluster. And so spectroscopy, high-resolution spectroscopy, will really be key in order to kind of tell the difference between those kinds of systems in the next era of surveys. And finally, just really briefly, I'll point out that there are constraints on the total number of satellites and on the slope of this function can actually differentiate between the predictions of different hydro simulations that have different prescriptions for subgrid physics and then for feedback and so on. Okay, so I just want to kind of wrap up, draw one more connection, and then I'll move on to the implications for dark matter. So there's been a really interesting line of work that has connected these measurements of ultra-faint galaxies in the local universe with their progenitors at high redshift. In particular, if you can measure or infer the star formation histories of extremely faint galaxies, then these measurements of their abundance at low redshift actually tell you about what you expect the high redshift galaxy luminosity function to be. And the really interesting thing is that if you make an assumption about the high redshift luminosity function that it's a very steep power law, then you actually don't correctly predict the observed abundance of satellites today. So what this means, in other words, is that these measurements of extremely faint galaxies are giving us constraints on the high redshift luminosity function, and in turn on the kind of population of galaxies that reionize the universe. So this is a really exciting line of work. It's something I'm thinking about now very actively. Okay, and one more word about the galaxies themselves. So there's often a question that comes up about how kind of typical the Milky Way is in terms of its satellite population, for example. And so this question is being answered empirically in a really kind of rapidly developing field of satellite surveys. So I'm showing you one example of this kind of survey. So the Satellites Around Galactic Analogs, or SAGA survey, essentially tries to find Milky Way analogs in the kind of local universe, so within 40 megaparsecs, and to measure their satellite populations. And the initial results of that survey, which is consistent with the results of several kind of surveys of satellite populations in the local volume, implies that the Milky Way satellite luminosity function is actually extremely typical among Milky Way brightness galaxies or among Milky Way mass halos. And so that's good news. It means that the inferences that we're drawing, for example, about dark matter physics, as I'll describe now, are not biased by the kind of peculiar characteristics of the Milky Way. Okay, so this is, as I said, this galaxy halo connection. I can kind of fill in like a cartoonish way the region that we've constrained in this work. Of course, the error bars are very large because we're only measuring this with one system, but they will continue to improve as we detect more satellites and as we kind of extend this formalism to use dwarf galaxies within the local group. But the really key thing is that we find no evidence of this cutoff in galaxy formation. And what that means is that we've set a limit on the mass of dark matter halos that we think must exist, right? So this number of 3 times 10 to the 8, or roughly 10 to the 8 solar mass halos that we've derived as the minimum halo mass means that those systems have to be produced by dark matter density fluctuations. So just to show you the ways in which this can discriminate between dark matter models, these are 2 simulations. A cold dark matter simulation on the left, in which there's no cutoff, right? So they're halos down to arbitrarily small masses. And a warm dark matter simulation, so this is a 2 keV sterile neutrino on the right. And of course, the free streaming of that sterile neutrino wipes out, right? It suppresses the abundance of subhalos below some critical mass scale, right? And so if we associate, right, if we think of associating those halos with galaxies, right, our limit on the minimum halo mass implies that dark matter can't be too warm, for example, and I'll show you what its other implications are as well. Okay, so just to make this kind of more explicit, as I said, right, if dark matter is warm, that's probably the kind of simplest example to think about. If dark matter is warm, so for example, if it's, if it has mass of the order keV and it's produced thermally, then its free streaming leads to a cutoff in the matter power spectrum at a characteristic scale. And that cutoff is kind of imprinted on the halo mass function or the subhalo mass function at the corresponding mass scale. But the interesting thing is there are many other examples of dark matter physics that also lead to a cutoff that's at least qualitatively similar. So what I'm showing you here is actually the case of WIMP CDM, which does have a cutoff. It's just at extremely small scales. So the idea is that if dark matter is coupled to the standard model, then in the early universe, heat and momentum are transferred between the photon baryon fluid and the dark matter. And in particular, the modes that enter the horizon while that scattering is efficient have their growth suppressed. And that leads again to a characteristic cutoff scale in the linear matter power spectrum, which structural formation kind of translates into a cutoff in the halo or the subhalo mass function. So for WIMP CDM, right, this cutoff is at extremely small mass, at roughly Earth mass dark matter halos. But I'll show you models very soon in which this cutoff is actually moved to observable scales in which we can therefore constrain. And so finally, this case of fuzzy dark matter has gained quite a bit of interest in recent years. So the idea here is that if dark matter is an extremely light particle, so of the order 10 to the minus 22 eV, then its de Broglie wavelength is actually astrophysical in scale. It's roughly a kiloparsec or so. And this leads to kind of interference effects on the corresponding length scales that, again, suppress the growth of structure on those scales. And so this is shown here in terms of the matter power spectrum, again, translated into, say, a suppression in a subhalo mass function, which can register at the characteristic scale, that clearly we can constrain with these measurements, since it's roughly 10 to the 9 in this example I'm showing you. So we've developed this framework that really simultaneously constrains all these possibilities that I'm showing you at once using our Milky Way satellite measurements. And so the idea, as I said, is that this suppression of the linear power spectrum is translated into a suppression of the subhalo mass function that has been kind of derived using high resolution simulations. And then this registers as a suppression of the abundance of observable satellite galaxies relative to CDM. So a way of kind of stating our constraint in a model independent way is that the current satellite observations are sensitive to roughly 25% suppression of the subhalo mass function relative to CDM at this minimum halo mass scale of a few times 10 to the 8. And this directly leads to constraints on all of these dark matter scenarios. So in fact, these constraints, once the kind of ultra-faint satellites are included, turn out to be quite stringent. So for example, for thermal relic warm dark matter that I introduced before, which is kind of a standard in this field, it's a good point of comparison. Our constraint is a lower limit on its mass of 6.5 keV at 95% confidence. And this is, very comparable to limits that come from, say, the Lyman alpha forest or from the analysis of strong gravitational lenses or stellar streams and so on. But of course, the systematics are largely distinct. So this is very good news that all these measurements are producing consistent results. And so I think this is quite compelling because, we're kind of simultaneously constraining these very general paradigms for dark matter. So this is kind of the opposite of looking for dark matter under a lamppost, if you think about it in that way. Okay, so I'm going to talk about the constraints for specific kind of particle physics realizations of these different types of dark matter, just to show you how our measurements can inform and be complementary to other constraints on these. So for warm dark matter, a case that is, I'd say, most often considered, at least in the kind of more recent literature, is that of sterile neutrinos, and in particular, resonantly produced sterile neutrinos, which are, popular theoretically for a variety of reasons related to neutrino mass and so on. So this parameter space for this dark matter model is shown on the right-hand side here. So this is the mass of resonantly produced sterile neutrinos on the x-axis versus their mixing angle with standard model sterile neutrinos on the y-axis. So our analysis excludes these colored regions. You should think of everything to the left of the colored region as being excluded. And what you can see is that it rules out basically all of the entire remaining parameter space, at least for kind of well-motivated theoretical versions of this model at rather high confidence. In particular, there's been this claim of an interpretation of an X-ray line from galaxy clusters that is 3.5 keV energy. So this line has been interpreted as kind of the result of stereo neutrino annihilating, producing high energy photons. And this is actually ruled out at extremely high confidence by our analysis. It's also ruled out by some X-ray measurements, some new X-ray measurements. So this is good, right? It's a kind of complementary constraint, I guess, coming from kind of more traditional high energy astrophysics and from these structural formation constraints. So if you think about this in terms of structure formation, what it's telling us is that the free streaming length of the dark matter has to be smaller than the sizes of the halos that host these ultra-faint dwarf galaxies, so smaller than roughly 10 kiloparsecs. So in the case of interacting dark matter, as I said, traditional WIMPs are coupled extremely weakly and therefore lead to a cutoff at very small scales. But there are generalizations of the kind of WIMP paradigm in which that coupling does not need to be so weak. In particular, if dark matter scatters with baryons with kind of a larger scattering cross-section than the weak interaction, then there is a cutoff that's imprinted at actually quite kind of large observable scales. And we've actually worked out analytically what that minimum halo mass is. So the idea is quite simple. It's when the momentum transfer rate between the dark matter and the photon baryon fluid is comparable to the Hubble rate or drops below the Hubble rate, then that interaction freezes out and structure can grow again. So that equation actually can be turned into a kind of analytic prediction for the minimum halo mass that you expect to observe in such a model. Interestingly, there's actually this really nice correspondence between the transfer function, or between the suppression of the matter power spectrum in this interacting dark matter case and in warm dark matter, and in the thermal relic warm dark matter model that I showed you before. And so this is actually the correspondence we use to set constraints. In other words, we say, given a limit on the warm dark matter mass, we can rule out all of the interacting dark matter cross sections that are strictly more suppressed than that warm dark matter case. So this visualizes some of the constraints. So this is a parameter space of the dark matter mass on the x-axis. And on the y-axis, it's velocity independent scattering cross section with protons. And so there are a few very nice things to note about our constraints on the plot, which are again shown as the shaded regions. The first is that they're actually, in shape, they're very complementary to kind of terrestrial searches, right? To experimental searches for this kind of dark matter physics. So for example, to direct detection experiments. In particular, you see that direct detection is, at some point limited to searching for low mass dark matter particles. And the reason for that is kind of simply experimental. The energy recoil for these very low mass dark matter particles is very small and therefore very difficult to detect. Also at high cross sections, something different happens. At high cross sections, if you try to detect these dark matter particles directly, they actually scatter with the atmosphere, with the Earth, before making it to the detector. So in both of those ways, our measurement is complementary to direct detection results. There's no limit at low mass from the cosmological constraint, since the suppression in the power spectrum happens anyway. And similarly at high cross section. So relative to previous cosmological constraints, for example, there have been analysis of CMB power spectra in such models. Our limits improve by really several orders of magnitude, so up to three orders of magnitude. That can be understood as a result of the fact that we're probing much smaller length scales than those previous analyses. And I should just say there's really exciting work going on to kind of generalize these constraints. So the model that I showed you before was this velocity independent scattering model, or in the context of this slide, this n equals 0 case. So n here is the power law index of the velocity dependence of this dark matter proton interaction. And you can start playing around with this. Kind of model builders have different predictions for this velocity dependence. And the cases where n is positive, so in the cases where high velocity interactions are kind of enhanced, which, as I said, does happen in several particle models of dark matter, this improvement is actually even more drastic. So just to pick an example, in the n equals 4 case, relative to the CMB, this is really like a 7 order of magnitude improvement just from the analysis of the extremely small scales. So there's really kind of a variety of exciting work to be done, both to kind of understand this in detail and to understand the complementarity of these results with direct detection experiments. So this is actually work by an undergrad at USC, Karim Amari, who works with Vera Glusevic and who I'm working with as well in order to set these constraints. Okay, so finally coming to this fuzzy dark matter case. So this is a little trickier because I guess fuzzy dark matter is a less mature field than kind of other dark matter cases that I showed you before. In particular, there's still quite a bit of uncertainty about, for example, the halo mass function or the subhalo mass function in fuzzy dark matter, because it's very difficult to simulate this kind of wavy dark matter in a robust way. So what we do in this analysis is we make extremely conservative choices. Like, we kind of scan the literature, choose the least suppressed subhalo mass function we can find, and then try to derive a limit. And when we do so, we find that even 10 to the minus 21 EV is very robustly ruled out. So certainly this kind of canonical 10 to the minus 22 EV fuzzy dark matter is very, very difficult to reconcile with these observations. And as I said, this is conservative. So this limit, depending on your assumptions about the effects of fuzzy dark matter, can easily become 10 to the minus 20 or even more stringent. So this can be interpreted as a lower limit on the mass of ultralight axions, which are a popular kind of candidate for fuzzy dark matter. And there's a really, kind of interesting field of work to make these like limits more robust in the particle physics sense. So in particular, we expect axions to have self-interactions, for example, which are usually not included in these kind of predictions for cosmological observables. So that's a really exciting area. It's something I'm working on these days. And hopefully it's possible to make these constraints kind of more realistic in that sense. There's still many orders of magnitude to go. If we're coming at it from a low mass direction, there are many orders of magnitude to go until hitting like the kind of canonical QCD axion region of parameter space. But so I think that'll probably take kind of qualitatively different ideas to reach. So in terms of structure formation, we can think of this as saying that the de Broglie wavelength of dark matter has to be smaller than the sizes of the ultra-faint dwarf galaxies. So it has to be smaller than a kiloparsec, roughly. Okay, so just briefly, I'm going to start to wrap up. I just wanted to highlight a couple other types of dark matter physics that these measurements are sensitive to. And one of them, interestingly enough, is actually the epoch at which dark matter forms. In particular, if you try to have dark matter form kind of late relative to standard WIMP CDM, so after BBN, but of course before matter radiation equality in order to get the CMB right, then you sort of generically suppress power on small scales, again, in a manner that's very similar to thermal relic warm dark matter. So again, this kind of correspondence can be exploited, and if you do so, you find that this Milky Way satellite analysis yields quite a large improvement over current limits on the kind of formation redshift of dark matter. So in other words, this analysis implies that dark matter has to have formed at redshift higher than roughly 5 times 10 to the 6, which improves upon previous bounds from the Lyman alpha forest. And finally, so all of the paradigms that I've talked about until now kind of imprint at early times. In particular, they imprint as a suppression of the linear matter power spectrum. But there's nothing that says that dark matter can't do interesting things at late times. There are many models in which dark matter has interesting phenomenology at late times. But the cool thing is that, if that late time physics also suppresses the abundance of subhalos to some observable level, then those paradigms are also constrained by this kind of framework. So one very popular example of this is self-interacting dark matter, which has been, kind of claimed to solve some of the discrepancies on small scales in the past. And so what we've done is this very careful kind of simulation study of the impact of self-interactions, of different velocity-dependent self-interaction models on the abundance of subhalos in the Milky Way. And what we find is that many of these choices lead to extremely strong suppression in the subhalo mass function, such that they will likely be ruled out by our analysis. So we're working out the constraints in detail, but it looks, just as a forecast, it looks like this kind of analysis is sensitive to SIDM cross sections of the level of 1 centimeter squared per gram at these low velocity scales that we're probing with the Milky Way satellites. So this is really exciting, and hopefully these constraints will be out sometime soon. And the last example of this late time dark matter physics that can kind of impact the abundance of subhalos is that of decaying dark matter. This has actually been claimed, this has gotten some interest recently, because if dark matter decays to, say, a radiation component, then it actually injects energy into the expansion of the universe at late times, which can alleviate the Hubble tension. So that's what this posterior distribution in green is showing on the right here. This was actually a fit of the decaying dark matter model to the combined measurements of the expansion rate from the CMB and from local distance ladder measurements. But unfortunately, if you inject enough energy into the universe to do that, you also inject enough energy into subhalos to basically kind of completely dissociate them. And what this means is that there is, again, a limit, right, on this type of physics purely from the abundance of observed satellites. In particular, this estimate, we're working out the details now, but basically we think that dark matter with a decay lifetime shorter than 10 gigayears is disfavored, at extremely high confidence by these measurements. And this, visualized on this Hubble tension plot, really cuts off a lot of the kind of favorable region. So we're, again, working out the constraints with another undergrad, Sydney Mao, who's actually starting grad school at Stanford in the fall. So we're very excited about this, and hopefully, again, this will be out soon. Okay, so I've reached my last slide. Just want to summarize briefly the main points. So the lack of a cutoff in the abundance of observable ultrafaints down to this 10 to the 8 halo mass scale yields really strict constraints on galaxy halo connection and also on the physics of dark matter. And I find this really compelling because it informs really large variety of dark matter properties, from its free streaming length to its standard model coupling to even some of the more exotic things I showed you at the end. And so I think a really interesting area for future work is the joint modeling of various small scale structured probes. In particular, we can think about combining these measurements of satellite abundances with measurements of the abundance and kind of perturbation profiles of stellar streams, and also with these measurements of substructure in strong gravitational lenses. So this is something I'm working on quite a bit these days, and I think it's a really exciting kind of direction. So all these people, this is a huge amount of work that all these people contributed really a lot to. So I just wanted to flash their names up and thank them quite a bit. Okay, I'll stop here.
Okay, thank you very much, Ethan. Now we open the floor for questions.
Okay, considering that the search for the satellite so far is subject to bias because the different surveys have different depths. You mentioned that AHS-C, for instance, it's quite efficient in finding satellites in the relatively small areas it looks for them. Is there room for the number of satellites associated to the LMC and SMC to be a little bit overstated, considering that there are surveys like Maglite and Diaz itself, which are probing regions very close to these, to the clouds?
Yeah, so let me go back to my map. Yeah, so it's a bit of a tricky question. So I mean, the idea is that that kind of observational, let's say, anisotropy that's induced by the different depth of different measurements is accounted for in the analysis, right? Since we, for example, use different observational selection functions for pan stars and DES, like when we do the forward modeling, right? So that, in that sense, like the different depth should be accounted for. And we find that this LMC satellite result is I mean, pretty robust. I mean, I think the thing that makes it hard to escape the conclusion is really the proper motion measurements. Yeah, I mean, those are pretty precise. let me put it that way. And it does seem to be pretty strong just from a purely kinematical point of view that several of these are associated. But there have, yeah, I mean, it's still kind of an open question exactly how many are associated with the LMC, but I think there is strong evidence that at least some of them are.
Okay, thank you.
So Ethan, I have a question. So first of all, thanks for the very nice seminar. It was a very incredible work, and that's really impressive. And I have a student that is now working on some dark matter model. Actually, it's a generalized dark matter model. And of course, we were very interested in trying to use or trying to talk to you and see how we can interact to get constraints. But so I have a couple of questions. So first of all, what is the data vector that you're actually using to derive your bounds?
Yeah, so the data vector is the satellite luminosities and surface brightnesses. I guess in addition to the information about which survey footprint you're in. So if you like, it's really the position, luminosity, and surface brightness of the 60 or so satellites that we've observed.
Okay, so and just to have an idea, what is the size of the data vector?
So it's really just that. I mean, it's let's say 60 times 2 times, I guess, one additional binary piece of information about like DES or pan stars, right? So it's not very large. Yeah.
Okay. And the other question, what is the covariance matrix that you use?
Yeah, good. So I think that's actually related to Basilio's question. So what we assume, I should see if I have my slide about the likelihood. I may not, but yeah, unfortunately I don't. I have the posterior, but I can send this, of course. So the idea is that we write down a likelihood for satellites to populate this parameter space in each footprint, this parameter space of luminosity and surface brightness. And this is modeled as a Poisson process. And the assumption is that the different survey footprints enter the likelihood without covariance. So in other words, the total likelihood is essentially the DES likelihood times the pan-stars likelihood. That assumption, so the first thing I should say, the results seem pretty robust, that assumption. The kind of physical reasoning is that those LMC satellites, because the LMC is still falling in, those are mostly within the DES footprint. So there's not like a correlated over and under density in those different footprints. So yeah, it's quite simple in that sense, but it's a good direction to think of in terms of doing it kind of even more rigorously, I think.
So it's an analytical covariance matrix.
Yeah.
Great. And okay, last question maybe for the moment. Have you thought about combining this with other probes for the DES?
Yeah, so I certainly have. It's a little tricky for a few reasons. So just to give a concrete example, one line of work I've been trying to do is combine this with strong gravitational lensing measurements. So like Simon Birer's measurements, since he's at Stanford now, so we talk quite a bit. So the tricky thing is, having a model that jointly describes both of those tracers. In particular, there's a huge separation in mass scale between, Milky Way mass dark matter halos and like 10 to the 13 solar mass halos that the strong lenses probe. So the uncertainty is really in that extrapolation. And depending on how you do it, you can end up with very different answers. If you do something very naive and just multiply their likelihoods, that can be done, and we've done that. And of course you have improvement, but the question is like what degeneracies are being broken. And it's not clear right now. My feeling is that the degeneracies will be in terms of the kind of hydro modeling that dictate the subhill abundance in either case.
Okay, thanks. So is it okay if we get in touch with you at some point
Yeah,
to talk
please.
about generalized dark matter? Thank you.
Sounds great.
And send my regards to Nick Cochran. He was
Okay.
a student here in São Paulo.
Yeah.
All right, any more questions?
Well, okay, I have another question, which is, well, I guess it's more a comment. You mentioned that it's going to be pretty hard to say much about, stellar systems like Milky Way satellites that have, say, 100 stars or stellar mass of 100 solar. And you said that we're not quite there yet, but if you look at the size against luminosity plane, you clearly see that at very low luminosities, the two loci of clusters, star clusters and galaxies seem to be merging already. It's not so easy by just looking at the size and
Yeah, I mean, I totally agree. It's very difficult. So I mean, the way we try to get around that in this analysis,
distinction between the two classes perhaps is already a challenging task, regardless of what is the total stellar mass.
Yeah. So I totally agree. So in this analysis, the way we get around that is, we only use, right, in the data vector, we only use satellite galaxies that have actually been kinematically confirmed, by independent spectroscopic measurements. But I think in like the LSST era, this is really hard. So once we have 100 of these systems and we don't know, right, in the sense that you're talking about, based on their luminosity and size, we don't know like what their classification is. My feeling is that this has to be done probabilistically. I mean, you can model the kind of, rates of the different types of systems populating that parameter space statistically. And to do better than that really requires really a ton of telescope time, a lot of spectroscopic follow-up. So I think very soon this will become a difficult problem. I think right now we're kind of right at the edge of being able to, know the identity of enough of these systems to kind of have a usable sample.
Okay, thank you.
Okay, any more questions? So if there are no more questions, and seeing how we're upon the hour, I think we can wrap it up. Next week, we'll have 2 webinars. On Tuesday, we'll have an extra webinar on computing science with Kyle Chard from University of Chicago. And on Thursday, we'll have our regular webinar, science webinar with Dimitrios Tanoglidis from the University of Chicago as well. Thank you, everyone, for coming. And thank you very much, Ethan, for a great webinar.
Thank you.